Hello everyone and welcome back to my channel RGA Structure. In today's video, we will be working through another example problem focused on the analysis of T-beam. So let's dive into the problem. Here we are required to compute the design strength for the T-beam shown in figure below here, with strength of concrete is given 4,000 psi and the tensile strength of steel 60,000 psi. So if you can see here in the figure, we are given 30 inches the effective width of the planks, the thickness of the planks, and the effective depth of 30 inches, and we have the width of the weave 40 inches. The reinforcement, tensile reinforcement is also given 8 by number 10, a total of 10.12 square inch. So let's dive into the solution. First of all, we need to check the minimum reinforcement as per the ECI code requirements, that is in section 9.6.1.2. using the width as the width of this beam, beam. Then the first criteria for the minimum reinforcement is equal to 3 times the square root of the steel, the square root of the strength of concrete, times BD over Fy, and that is equal to 3 to the square root of 4,000 psi times 14 is the width of the weave times 30 inches over 60,000 psi the strength of steel, that is equal to 1.33 square inch. So the next requirement is should not be less than 200 BD over Fy, and that is equal to 200 times 14 times 30 depth over 60,000 psi, and that is equal to 1.4 square inch. So we need to compare it to the tensile strength provided. We have 10.12, that is greater than 1.4. So greater than 1.4. 1.4 is bigger than 1.3. So we are okay for the minimum requirements. The next one is to compute the value of tension force here in the diagram, showing all the parameters that we're gonna calculate later on. The value of C, A, this one here, C is equal to T. By the way, here, since we haven't checked the location of value of A, so we just express this in our equation to EC, which means the area of the concrete required in the compression stress. So determining the EC, that is equal to, EC is equal to T over 0.85 F sub C prime, which is equal to 607.2 kips over 0.85 times 4 psi, and that is equal to 178.6 square inch. So the plan's area, which is this one here, the width of the plan's is 30 times the plan's depth of 6 inches, so we have 120. That's why we have 120 here. And this is less than to area of the compression stress, which is 178.6. So it is obviously that portion of the area will be extended below the plans of the here, so within the depth of the weave. So the compression block must extend below the plans to provide the necessary compression area, which is the excess is 178.6 minus 120 square inch, that is equal to 58.6, this one here. So this is the area, the extra area that extended below the plans. So if we calculate this height, so 14 inches and y, if we divide this by 14 inches, we'll have 4.19. That is the height of this area here. Then, so this one here, 4.19. So now the next thing is to locate the centroid, because we have two elements here, the plans and the portion of area here below the depth of the weave. So if we recall the formula in locating the centroid of an area, that is the summation of f sub y sub I times the area all over the total area of this one here. So to calculate that one, we have 120 square inch times 2, 120. So our reference from the top, y bar from the top. So the centroid of this element is 2 inches. That's why 120 times 2. Plus the area of this one here, 58.6, times the area from the top to the centroid of this area, that is 4 inches, plus the half of that 4.19. So we have here 4.19 divided by 2. All over 178.6. That is the total area of that. So this is the result. The y bar is 3.34. So this is the location actually somewhere here. So 3.34. So within the plans, the location of the centroid of an area. So the next one is to determine the label arm Z, which is this one here, measured from the centroid of the steel to the location of the centroid of the compression area of the concrete. So the next one is to determine all these parameters, which is A, C, and the tension strain. So we have all the formula here. First of all, we need to calculate the A. So we have already determined the A value, which is 4 plus 4.19. So this is your height of A value. This one here. So the next one, we have already determined the value of A, so we can now determine the value of C. Value of C is the location of the neutral axis. So we have 8.19 over 0.85, that is beta. By the way, beta is controlled by the strength, the strength of the concrete. Beta is 0.85 if the strength of concrete is less than or equal to 4 KSI. The next one is the tensile strain. So by ratio and proportion, given C, given the value of the strain of concrete 0.003, and the depth minus C, so we will have this equation. Then substituting all this formula, this value, then you will get 0.00634, which is greater than 0.005. So this section is ductile, and I'm using of P equal to 0.9, and Fy is equal to yield of strength is correct. So our assumption is correct. So the next one is the calculation of the design strength moment, which is equal to P times the nominal moment. So if we sum up moment here, to the centroid of the compression stress, we will get the TS times Z. This is the one. Then times P. So the equation is PTG. So 0.9 times the tensile force, which is 607.2, times the 26.66, the moment arm, so it's equal to 14,569 kip inch. So we convert that into kip's foot. This is the one. So 1,201 1/4 Cape speed. So that is our design strength. So right, so that is the final answer. So that concludes the solution to our problem. So thank you guys for watching. And if you found this video helpful, please don't forget to like and subscribe. See you next time. Take care.